So now with this one, if you have a set of eigenvectors for this Hermitian operator, then we can do something called diagonalization. So if we choose this as our basis, choose this eigenvector as our basis, we'll be able to diagonalize the operator H. And we found that after diagonalization, so it means H is now in the new basis, the matrix for this, using this set of basis, is a matrix that only have diagonal elements. And all diagonal elements are just eigenvalues. Okay, so that's what we call diagonalization. And it's obviously useful for quantum mechanics, but in other physics problems, the same method apply. So like what we did before the potential problem, you can also do this diagonalization problem, because remember that the two eigenvectors are orthogonal for the potential problem that we did at first. So we can do the same diagonalization also. Okay. And so what we'll do is just write down the form and then show the procedure how you do this normalization, orthogonalization, diagonalization. All right, so and the idea is you have this, you have, I have to erase that, but that doesn't matter. So H, C sub I, S lambda sub I, C sub I. Now, after this method, if they are degenerate, you use the Gram-Schmidt method to generate eigenvectors such that they are all orthogonal to each other. So it's possibility that C sub J, C sub I are just conical delta. Okay, assume that we could do that by Hermitian operator H. Right? And now the idea is that this is all treated like column vector. This C sub I is all column vector, so that you have you could have infinite many of them or finite number of them, depends on the dimension of your H, right? And now we want to do so. If you H operate on, so you put all these eigenvector into, but each of them is a column, right? If you put it and put all these columns together, it forms a square matrix. H operate on this square matrix, and each column is one of these eigenvectors. C sub 1. The first column is C sub 1. The second column is C sub 2, and then so on. C sub n. And if infinite dimension, yeah, infinite. So put all the column vector, this eigenvector, together and form a square matrix. Is that okay? The first procedure. Now you H operate on this H operate on this matrix, and obviously by this line, by this eigenvalue equation, that becomes the same. That becomes still a square matrix, but each column is different now, because H operates on C sub 1, the first column, give you lambda 1, C1, right? That's the first column. The second column is the lambda 2, C2, and so on. And then you have the n column, lambda n, C sub n. Right? And this is always true even for the degenerate or non-degenerate cases. All these lambda can be the same or not the same, assuming we already normalize everything, right? And this is still true. H operated on this matrix becomes this one, right? Now, if you do a scalar product of this object with another eigenvector, right? And you see, so that becomes a this any vector C sub j of this H operating on this matrix. Right? Obviously, that because of this relation, they are orthogonal. So this C sub j we only pick up. So all these will be zero. All these there will be a lot of zero columns, zero vector. All these will be zero, except the j column. You have a lambda j, and that's the scalar product will be 1. This is just j, and the rest is 0. Right? That is let's just say this is it's a column vector multiplied by a square matrix, right? So it's actually just a column vector. This is not a matrix, right? This is up to yeah, right. And then now if you call instead of just one vector, you put all these C sub j into a row, each row. So the first one, lambda is just a value. Lambda is just a value. Yeah. Now the next step. This is just one vector, so we can put the C sub 1 here, C sub 2 here, C sub n here, and so on. H and operate on this one. C sub 1, C sub 2, C sub n. Okay, and you realize that this matrix is just basically the transpose, and then for the value, you need the transpose and then the complex conjugate. Basically, this is the Hermitian matrix of the second one. The left is the Hermitian matrix of the first one, right? Then obviously, this one is just this one. And using the orthogonal property, just like this one, if each row multiplied by this one will give you just one value, right? And then obviously that will give you just a diagonal matrix. So number 1, number 2, 0, all 0, number n, and the rest are all 0. Right? You see that? So because this one multiplied with this one, say the first one, the first row is just C1. The first element is this one, and the scalar product of this one and that one, C1 and C1 will give you 1, so you can lambda 1. The second column is this one and that one, which give you 0 because of orthogonal and so on. Everyone else is 0. So the second row, this one, up, and this one, the scalar product will give you 0. And the second one is this one, and that one give you lambda 2, and the rest are 0. And then so now this becomes a square matrix with only diagonal elements. And now you realize this is of a form of unitary transformation, right? And we call that U. We actually call that U. And this is our U dagger, actually, or U dagger. But you realize that U and U dagger will form like that. U and U dagger is just an identity matrix because you get rid of this H, this matrix multiplied by this matrix will give you just a diagonal element with all 1, right? Because of this relationship. So you have this relationship. So this matrix formed by the column vector of the eigenvalues, or the row vector of the eigenvalue, they are unitary matrix satisfy this U and U dagger is one. As a unit, as identity matrix, or you can say U dagger is just your inverse, right? And so, so this becomes U dagger, and that is what we call the H prime. After diagonalization, the original operator you sandwich using the procedure to do the unitary transformation U dagger. That's what we did to transform a operator, and we show that these are unitary matrix. So this will give you the transformation, and basically this will transform your basis from this the original basis, whatever this the original basis, and then transform to the basis using this C sub I. Using this eigenvector, normalized eigenvector as your basis, and therefore this in the new basis, this operator has only diagonal elements, and our elements are the eigenvalues. Okay, and that's the property of the Hermitian operator. You can diagonalize it using this procedure. First, solve for all this C sub I, and then normalize them so that they are form of a normal set. And then you form this U dagger matrix by all these column vector, and form this U matrix by all this row vector, and then sandwich it in the operator, and now you transform your operator into a diagonal matrix. Okay, so that's the procedure. And
symplectic transformation. The symplectic transformation.
That is, I think that is a different concept. I think that is simplicity is preserving the area, right? And it may or may not. I mean, it depends on what H is. This is an arbitrary operator. It doesn't have to be. Or the way it's writing is, it doesn't have to be a Hamiltonian, right? It can be any operator. That and this is the procedure. It's just saying that any Hermitian operator, you can go through that and diagonalize this operator in the basis of the eigenvectors, and then in the new basis, the operator is diagonalized. The matrix for the operator is diagonalized with the elements being the eigenvalues. So that is the property. And what's time we have? It's okay. So that's how you do it. Maybe a quick example. A quick example before we move on. This is a little bit abstract, but an example will make it clear. Again, this example is a simple one with a 3x3 matrix. And first you solve for the eigenvalues and eigenvector. We just use the same procedures, so minus lambda 1 0 1 minus lambda 0 0 0 2 minus lambda. You get the characteristic equations. So you have 2 minus lambda square minus 1. So you have 3 eigenvalues. Lambda is 2, 1, and minus 1. Right? And now So lambda is 2, there's minus 2, 1, 0, 1, minus 2, 0, 0, 0, 0. XYZ is 0. Then again, obviously, you can choose XYZ as just 0, 0, 1. Right? But that's the first eigenvector. And this is lambda equals to 2. Now lambda equals to 1. We have minus 1, 1, 0, 1, minus 1, 0, 0, 0, 1. So again, z is 0 because of the third equation. The first two give you x equals to y. So x, y, z is, so x equals y. You can choose 1, 1, 0. Right? And you normalize that. And lambda is minus 1. And now it's 1, 1, 0, 1, 1, 0, 0, 0, 1, or 3. Z is 0. Again, the z is 0. X is equals to minus 1. So we choose up to a sign 1, minus 1, 0. So you have three eigenvectors, this one, this one, this one. Now you can check whether they are orthogonal. So obviously this dot into that is 0, this dot into that is 0. This dot into that is also 0 because this is 1, this is 1, 1, this is 1 minus 1. So they're all orthogonal, right? So, and it's possible because the original matrix is symmetric. So it's symmetric is Hermitian because all the real element is real, so you don't need to take complex conjugate. It's just the matrix being symmetric. Okay, now you can, the procedure to diagonalize the H is choosing U, so U dagger using the procedure. U dagger is just putting all this column vector together. So, so this is the first one is 0, 0, 1. The second one is 1 square root of 2, square root of 2, 0. And the third column is 1 square root of 2, minus 1 square root of 2, 0. Okay, is that okay? So this is your dagger, U dagger, right? And then once you have U dagger, U is just the complex conjugate of the transpose. So we take the transpose is 0. 1 over square root of 2, 1 over square root of 2, 0, 2. Right. And this one is minus 1 over square root of 2. Right. And this one is this one. So, right. So 1, 0, 0, 0. Right. This is the transpose with symmetric, right? Yeah, okay.
That's
So this,
the order in which we write the eigenvectors.
that doesn't matter. You still get the diagonal matrix. Only the element will be exchanging the eigenvalue in the elements. So the diagonalization is only up to an arbitrary order of the eigenvalues. So you can exchange the column, and then finally the H prime will be different by the eigenvalue. The elements are exchanging different row, a different column. Okay. Okay, so we can do the H prime. H prime will be U H E dagger, right? You can see which one we can do first. So UHHs, U, 0, 1, 0, 0, 0, 0, 2. And U vector is this 0, 0, 1. I mean, this is just to check it explicitly. We just did the general formula, so you should expect it to work out, but we'll just check it explicitly. So this U is this one. And then this is the product of this one, so now you just need to do a matrix multiplication. This times that is 0, right? This is and this times that is just 1 over square root 2. And then this time that is minus 1 over square root 2, right? And then this one, this time that is 0. And this time that is 1 square root 2. This time that is 1 square root 2. And finally, this time that is 2. This time that is 0. And 0. Okay. And now finally, hopefully work out. Right? The first element, this times that is 2. Then this time that is 0. This time that is 0. The second one, this time that is 0. This time that is 1/2 plus 1/2 is 1. This time that is 0 because one is different sign. And this time that is 0, obviously. This time that again is 0 because of changing sign. The last one, this times that is minus 1/2 times minus plus 1 minus 1 is minus 1. Okay, so X prime is given by the diagonal element, diagonal matrix with the elements are the eigenvalues. This is 2, 1, and minus 1. Okay, so that's the procedure, which is supposed to work out even if we don't do it explicitly, because this is built from the procedure, the recipe that we developed, and that should work. Right? The next topic is what we call the simultaneous diagonalization. So for this Hermitian matrices, if you have two of them, two diagonal, two Hermitian matrices, you can use the same basis to do diagonalization, provided they commute with each other. So, just looking for the form of the textbook didn't write down the form of the eigenvalue problem. Again, the eigenvalues are these little a's of I and b's of I. So okay, so this you have two operator A, have the A, have the B, right? And then so like just write down separately. I think textbook didn't write it down. So A times this eigenvector C sub I is this. Let's make it explicit. This is vector, and this is A sub I. This is the eigenvalue C sub I, and B C sub I. B sub I, C sub I. Okay, if they have the same set of eigenvector, they may have different eigenvalues. So one is A sub I, the other B sub I. Then the condition that they can have the same eigenvectors we operate it on different orders of B, A, C sub I. So this one is this one, so substitute this in this, the B, A sub I, B sub I. And that will give you B sub I. This is this one. This after you take the A sub I out, this is just number. You get A sub I, B sub I, C sub I. And then you reverse the order, A, B, C sub I. You see that is A, B sub I, C sub I. And then using the first one is still the same, A, B, C sub I. Right? And this is for arbitrary eigenvector. They are all the same. So in order that this is the same, the B, AB must be equals to BA, or the commutator is 0. Okay. Okay, if A and B are commute, then they can have the same set of eigenvector. If they have the same set of eigenvector and they have Hermitian, so all these eigenvector can form basis to diagonalize your matrix or your operator, and you can use the same diagonal matrix, use the same U or U and U sub U dagger, use the same U and U dagger to transform both A and B to diagonal matrices, right? Because they are both the same. They are eigenvectors of the same operator. I mean, of both operators. Okay, so that is this topic, and that is useful. That is useful for because that very common that you have operator that commute with each other. Like when you do quantum mechanics, not all the operators are not commute with each other. Many combo operators commute with each other, and so they can have the same set of eigenvector. Okay, and the next one, it's just the other way to write after you use the eigenvector as your basis to do expansion. Then you can write the operator formally as your basis of H. Because after you diagonalize it using this C sub I, whatever C sub mu as the eigenvector, then you can write it like, and the elements of this diagonal matrix is the eigenvalue. This is the way it is. Remember this at the general operator. What we did is summation mu and summation mu. We have phi mu and A. Is it A mu nu? Let's figure that out. A mu nu. Phi mu. Well, you need to sum over that. So A mu nu is usually defined as phi. Sandwiches in the right hand side is mu. Yeah, that's it. Yeah. Right, but now because they are diagonal, after you do use eigenvector as basis, instead of phi you use eigenvector. Now it's diagonal, so this double summation becomes just sum over diagonal elements. And the diagonal elements are just the eigenvalues. But this is the form of the operator formally. You can write it like that. Okay. Now if you have another operator that is commute with them, commute with it, then the trivial one is just a function of this operator itself, like a H and H operator on H. That becomes H squared. And then obviously the eigenvalues of this one is lambda square. So that becomes lambda mu square. And you can generalize that to any power n. So mu lambda mu n, right? Because this operator xn is just operate xn times. Each time you operate on one of these eigenvector, you pull out the eigenvalue lambda mu, and you operate n times, you pull eigenvalue lambda mu n to the power n. Okay, so that's formally you can write it like that, and any function of this operator which has a power series expansion, now you can just write it like so mu f using the function lambda mu in here. Okay, that's just straightforward, because if it has a Taylor expansion like each term has the power h to the power n term, and each one will just change h to the n to lambda to the n. So you combine all the terms, you get back to the same function using the argument, the eigenvalue as the argument. Okay, so that's the way it is. And then similarly, if h is c sub I, c sub mu, doesn't matter. The text is it's lambda mu c sub mu, right? Then obviously, if you multiply the inverse of h c sub mu equals to lambda mu h inverse c sub mu, and that's just identity matrix, or just one. You can say that. You can say h inverse of c sub mu as 1 over lambda mu c sub mu. Right, so in that case, h inverse is this 1 over mu 1 over lambda mu. Okay, so that this property. Now came the equation that in chapter 2 there's an equation. Let's get rid of this. This equation 1.84 is stated there without proof, and that is the statement that for Hermitian operator, the determinant of the matrix exponential function of A is the product of all the exponential of lambda mu. Right. So for Hermitian matrix, the determinant is invariant, right? We already talked about it's invariant to unitary basis transformation, right? And then so you can always diagonalize your A matrix with that they are all diagonalized, and this A has the eigenvalue lambda. So E sub A has the f, E sub A is of f. The eigenvalue f evaluate at the lambda. In this case, e to the power, e exponential lambda mu is the eigenvalue for this operator e to the power a, right? So And because it's diagonalized, the determinant is just the product of all the diagonal elements. We sum, not sum, multiply all these diagonal elements and give you this one, right? And then obviously this product can be equal to exponential sum over mu, lambda mu, right? Because this property of exponential function, and this sum is just basically is a trace of this is exponential function of trace of the element A. Because the trace is also invariant. We just did that before. The trace is invariant to unitary transformation to the sum of the lambda. After you diagonalize that, the trace is the sum over all the lambda. And so that's the equation, right? Determinant of the exponential A, the matrix, is the exponential function of the trace of the matrix. Right? And that's this equation. All right, so that use a lot of mathematical property that we did before. Okay, see, let's finish up before we go, finish up this 6.4 section. Exponential, expectation values for the Hermitian operator. Now because it's, so you have a psi and h and psi, right? And then, yeah. If you're using the psi in your basis using the eigenvalues of h, eigenvectors of h, then this h is diagonalized. So psi is sum over mu, a mu of this basis, whatever you call it, c mu, right? And then this expectation value obviously just sum over mu because it's diagonalized. So it's just a mu square and all the lambda mu, right? And if psi is normalized, then sum over mu a mu squared is 1. So it's like you sum over all of them equals to 1. So this coefficient in this basis is normalized. So each one of them is represent a partial fraction of 1. Right? It add up to 1. And sometimes in quantum mechanics, you interpret that like a probability. So because all the probability will add up to 1. So all the square of the coefficient becomes a probability. And now this, for whatever the operator, the expectation value is just this probability multiplied by the eigenvalue of this operator for that state, for this for the eigenvector. And this like a weighted average of the eigenvalues. Right? So that is this. And there's some implications, say if lambda has either maximum or minimum, so you can say that so if it has a minimum, so this value must be, the expectation value must be greater than the lambda minimum. If all the eigenvalues has a minimum value, then the smallest of this expectation value is 1. So basically, or everything else is 0 except the smallest eigenvalue is 1. Then you get this one, right? Otherwise, it's always greater than this one. And likewise, this will be smaller than if it has a maximum value, right? That's just it's just straightforward application, and that also apply to this so-called positive definite matrix. If the matrix or this operator has all eigenvalues are positive, then it's called positive definite matrix. Okay, and obviously then if all the eigenvalues are positive, then it means that the expectation values are all positive. So that's the consequence of this positive definite matrix. Okay, and I suppose I'm out of time, but anyway, I think there's one last example. This overlap matrix basically is a basis using non-orthogonal basis, and then you can define this overlap matrix, and show that this overlap matrix is also a positive definite matrix. The reason is that they're expressing the same state, and the magnitude of a state, the scalar product of a state with itself is positive. It's always positive. So the overlap elements are all, the matrix is positive definite. Okay, so that is in straightforward example. So we're done with the 6.4.